Okay, section 8-3 is about trigonometry, which the word trigonometry, the trigonometry, means a triangle, and metry means to measure. So trigonometry means to measure triangles, specifically right triangles. We'll be looking at angles and side lengths in right triangles and using one to find the other. Here's an activity that could be done in class. Have every student draw a right triangle with one angle that measures 65 degrees. Now, I'm not using a protractor, but I'll kind of sketch what it might look like. Here's a right triangle, 65 degrees. Now, students will draw large or small or different sizes of triangles, but there are some ratios that will stay the same. So looking at the 65-degree angle, this side is the hypotenuse, and this side is the adjacent leg. Again, adjacent means next to. So it's the leg that's next to the 65-degree angle. This side is called the opposite because it's the leg on the opposite side of the triangle. Okay. Again, the triangles could be bigger or smaller, but as you measure these lengths and look at the measurement of the opposite over the hypotenuse, the adjacent over the hypotenuse, and the opposite over the adjacent, those ratios will stay the same. And the reason is because no matter how big or small this triangle is, these triangles are all similar to each other. And so their internal ratio stays the same. Let's look at the Geometry Sketchpad file to kind of look at this in a different way. Here is a right triangle. And as you see, I've measured the opposite over the adjacent ratio, the adjacent over hypotenuse ratio, and the opposite over the adjacent ratio. Now, as I change the size of the triangle, angle A is not changing. It's staying the same. And the ratios are staying the same. Again, because all these triangles are similar to each other by angle. If I change the angle, then the ratios change. So again, when the angle stays the same, the ratios stay the same. When the angle changes, the ratios change. Okay, these three ratios are so important and so used that they've been given names. Okay, the opposite over hypotenuse is called the sine ratio. The adjacent over the hypotenuse is called the cosine ratio. And the opposite over the adjacent is called the tangent ratio. These are very important ratios, and these are three types of trigonometric ratios. Okay. Now, a way of remembering these, as they're important to remember, is often by taking the first letter in order. We spell a funny word. Okay? So-ka-toa. So-ka-toa. It's a funny word, but it can be used to remember what the sine, cosine, and tangent ratios are. And again, they're in order. The sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. So-ka-toa. All right, so here's an example. We're looking at side A. Okay, looking at A, let's see here. So-ka-toa. Looking at A, the 5 is the opposite because it's on the opposite side of the triangle. The 12 is the adjacent because it's the adjacent leg. 13 is the hypotenuse. Okay, so the sine is the opposite over the hypotenuse. It is 5 over 13. The cosine is the adjacent over the hypotenuse, so it's 12 over 13. And the tangent is the opposite over the adjacent, or 5 over 12. Feel free to leave those as fractions. Okay, another example. Now this one's kind of turned a little bit differently. Let me move these down. We're looking at angle B this time, and this is my right angle. So just to help us out, 24 would be the side that's adjacent or next to the angle. 7 would be the opposite side, because it's on the opposite side of the triangle. And 25 would be the hypotenuse, the longest side. Okay, again, SOHCAHTOA. So the sine is the opposite over the hypotenuse, 7 over 25. The cosine is the adjacent over the hypotenuse, 24 over 25. And the tangent is the opposite over the adjacent, 7 over 24. Okay. We talked briefly before about this relationship between when the angles changed, the ratios changed. When the angles were the same, the ratios were the same. Now, back in the day, BC, before calculators, there used to be trig tables printed up in geometry textbooks. Lucky for us, our calculators have been programmed to have those ratios in them. So if you look at most calculators, there's a sin, cos, and tan, or sine, cosine, and tangent buttons that can be used to find these ratios. Now, one thing to check is make sure that it's in degrees and not radians. Okay, so if you grab your calculator, we can find these ratios. Okay, for the sine of 64, we type in sine 64, and we get the ratio, the sine ratio for a triangle with an angle of 64 degrees. I usually have at least 4 decimal places on trig ratios, just because they're pretty important and I don't want to round off. For the tangent of 77, you type tan 77, enter, 4.3315, and the cosine of 33 degrees is 0.8387. Now let me point out that on a graphing calculator, you'll type in the tan, sine, cosine, those buttons first, and then type the angle. In most non-graphing calculators, a scientific calculator, you'll type the angle first and then press the sine, tangent, or cosine button. All right, now using these ratios is where it all comes together. So here's a triangle. I know one angle and one length, and I can use that to find any other length here. For example, I'll start with this one. If I wanted to know length CB, now I know the adjacent. I want to find the opposite. Let's see here, SOHCAHTOA. I got to find the ratio that relates opposites and adjacents. Now, opposites and adjacents are like the tangent. So the tangent of 35 degrees is equal to the opposite over the adjacent. Okay, now I will make this into a proportion so I can solve it. And I cross multiply. 1 times x is x, and 5 times the tangent of 35 is 5 times the tangent of 35, which I grab my calculator and type in 5 times tangent of 35. And I get the length. This length is 3.50. Okay? Another type of problem is if I wanted to find the hypotenuse, which I'll call y. Now I could use either the sine or the cosine since I now know the opposite length, but I prefer to stick with the adjacent since I know that one to be exactly 5, and where x I kind of rounded off a little bit. So the trig ratio that relates the adjacent and the hypotenuse would be the cosine. So the cosine of 35 degrees is equal to the adjacent 5 divided by the hypotenuse y. Again, I'll put over 1, make a proportion, cross multiply. 1 times 5 is 5. Cosine of 35 times y is cosine of 35 times y. Now I want to solve this equation for y, so I'll need to divide both sides by the cosine of 35, which I know feels a little funny, but just think that cosine of 35 is still a number. So I'm dividing by the ratio, the number, that's cosine of 35. And then I take my calculator and do 5 divided by the cosine of 35, and I get the length of the hypotenuse, which is 6.10. Okay. Another example problem, if I know the hypotenuse to be 9, I could find either the height or the length of this triangle, either of the legs. I'll just pick this one. So it's SOHCAHTOA. Now, so here I know the hypotenuse. I want to find the opposite. So what ratio relates opposites and hypotenuse? Well, it'd be the sine. So the sine of 48 degrees is equal to the opposite over the hypotenuse. Okay, put over 1 and I cross multiply. X times 1 is x. 9 times the sine of 49 is 9 sine of 49. So I grab my calculator and type in 9 times sine of 49. I'm sorry, 48. Okay, and I get x is equal to 6.69.